You've learned the theory behind time-of-flight mass spectrometry, but when it comes to those sneaky exam questions, it can feel like a different story altogether. In this video, we're going to tackle some real exam-style questions together. I'll talk you through exactly what the examiners are looking for, where students typically slip up, and how to structure your answers to pick up every possible mark. We'll cover everything from writing ionisation equations to calculating time of flights. And yes, we'll clear up those bits that always seem to trip people up. So grab a pen, pause the video when you need to, and by the end, you'll feel way more confident facing any mass spec question that comes your way. So one idea to make the most of this video is to make sure you pause the video and have a go at writing the answer yourself, writing it down or speaking it out loud rather than just thinking it, before we then go through the answers together. So here's our first one. This one is about writing ionisation equations. You can see the first one is two equations for ionisation by electron impact. The second one is to do with electrospray ionisation. So pause now, have a go. If you can't remember, then head back to the previous video where I go through this stuff from scratch. Okay, so here's the answers. Now, what you need to remember here is that all of the ionisation takes place in the gas state. So all of your atoms and ions and molecules need to have that state symbol of gas. Now, the first two for electron impact, remember what happens is you have high speed, high energy electrons from the electron gun knocking into each of the particles and knocking an electron off. That electron is shown on that right-hand side. So that's a plus E minus, i.e. one calcium atom makes a calcium ion and that electron that was knocked off. And you can see the same there for the ethane, the C2H6. If you knock one electron off, one negative charge leaving, then it means that you have a 1+ ion. The second one though, electrospray ionisation, may have caused some issues if you were wondering about where does that hydrogen ion go? Where does it come from? Where does it go? So for electrospray ionisation, remember, you are dissolving your sample into a volatile solvent. It then passes through a hypodermic needle with high voltage, and we have protonation, meaning each of those molecules will accept 1H+ ion, and 1H+ ion is the same as a proton. So we have the +H+, and you can write that as part of the molecular formula. So rather than C2H6O2, it goes to C2H7, there's the extra proton O2. And then because the proton, the hydrogen ion is a 1+ ion, that is also a 1+ charge. So here's our second question. This one is about explaining why different ions would have different time of flights. So have a read, hit pause, and then when you're ready with the answer, play and we'll go through the answers together. Okay, so the key ideas you are looking for here for 2 marks for this first one is that the idea first that lighter ions travel faster. Because remember what happens during acceleration, all of the particles receive the same kinetic energy. And because they have the same kinetic energy, it means that the lighter ions can travel faster than the heavier ions. You also need to link that through to the fact that this is time of flight mass spec. What we're doing here is we're measuring the amount of time it takes for these ions, lighter and heavier, to pass along the tube. So the first mark, the lighter ions travel faster or heavier ions travel slower. The second mark, and therefore takes less time to reach the detector. And then the next one is a reiteration of that question. So here you need to remember, first of all, that if you are stating which species is reaching the detector first, you need to have the mass number, the element or molecule formula, and the positive charge. So we're not saying 79, we're not saying 79Br, we're saying 79Br+. That's the whole species there. And that one will reach the detector first because it is lighter than the 81Br+, and therefore will travel faster. Now the second one, so there we have methane, CH4. Those 12 and 13s, those are referring to the mass numbers. So we have that, a carbon 12 and a carbon 13 in the other species. So the carbon-13, that is a heavier isotope. So therefore here, the 12 carbon, 1 hydrogen for methane molecule, that is lighter and it will travel faster. Okay, here we have a mass spectrum. Now this is where a little bit of mass can start to creep in. So this question is asking you to calculate the relative atomic mass. Have a read, have a go, and then hit play when you're ready to have a look at the answers together. Okay, so for this first question, or part of the question, what isotopes are present in this element? What we're doing there is reading off the x-axis, which is the mass to charge ratio. Now, because gallium is an element, it was ionized via the electron impact method. So therefore, we take the mass and we divide it by that +1 charge. So in our case, therefore, here, the mass to charge ratio, mass divided by +1, is the same as the mass. So we can just read off 69.0 and 71.0. In order to get the marks, you need to have given the 69 and 71 as superscripts. So those are the mass numbers, and then the formula of the GA correctly, capital G and little a. For the second one, we're calculating the relative atomic mass. Now the way to do that is to try and find, first of all, the total mass of all of the isotopes added together. That's the first line of that working there. So what we do initially is we take the 69, the mass of the first isotope, and multiply it by how much we have of it, 60.1. We then add that to the mass of the second isotope, 71, multiplied by how much we have of it, 39.9. Then, once we have the total mass of all of those isotopes, you divide that by how much of the isotopes we have in total. So those are the relative abundances added together, the 60.1 and 39.9. That gets us to our overall answer of 69.8. But the question does say, give your answer to the appropriate number of significant figures. And you might be thinking, why is it 3 sig figs? Because it's not always 3 sig figs. The clue comes from the question. We have to look at the data we are working with. So the data you can see there, those mass to charge ratios are given as 69.0, 71.0. That 0.0 counts as a significant figure, and that's why it's 3 significant figs. So for the next question, we're just going to have a quick reminder of the equation that we are going to be using. So we have kinetic energy equals 1/2 multiplied by m, the mass in kilograms, multiplied by velocity squared. The other thing to notice there is that kinetic energy is in joules. Let's use this for our next question. So this question is about calculating a time of flight for a particular isotope of oxygen, oxygen 18. Pause the video now, have a good read of the question, have a go, see how far you get, and we'll go through it next. So the first thing that we're going to start off with here is finding the mass of 1 mole of oxygen. Now, the mass of 1 mole is equal to its MR in grams, so we have 18 grams. Then, to find the mass of 1 atom, we divide by the number of atoms in a mole. So dividing by Avogadro's number, 6.022 times 10 to the 23. That takes us from the mass of a mole to the mass of an atom. Now, bear in mind that this is coming out in grams. So we then have to divide by 1,000 to turn it into kilograms, which is what our equation needs. Mass is always in kilograms. Now we can put our numbers in. So we're taking our distance and turning it into meters, 0.75 meters. We're then putting in the mass of 1 atom of oxygen in kilograms, then dividing that by 2 times the kinetic energy that was given in the question. That is already in joules, so we don't need to do any conversions with the units there. That then gives us 5.79885 times 10 to the minus 5. That's the full answer, but it's not our final answer. We have to consider significant figures. So read the question again and look at what is the smallest number of significant figures, because you can't give an answer that is more precise than the data that you first worked with. So 75.0 is 3 sig figs and 2.50 is 3 sig figs. So we give our overall answer to 3 significant figures. Okay, here is the last question we're going to tackle together for today. And this is where we have two different ions. So in this case, they are copper. So 63 copper isotope and a 65 copper isotope. We are given the time of flight for one of those isotopes, and our job is to find the time of flight for the other isotope. So pause the video now, have a good read of the question, see how far you can get, and we'll go through it next. Okay, so what we need to do first of all is manipulate the equation. So we have here two ions. They are both in the same mass spectrum, and therefore during that acceleration process, they are both given the same kinetic energy. Therefore, we can write that half mv squared for one of the particles is equal to a half mv squared for the other particle. Now, we don't want to keep this v in the equation because we don't have any information about that v. So we're going to substitute in velocity equals distance over time. So we're going to pop in distance over time for v. Then times out that bracket, so we end up with a half md squared over t squared equals a half md squared over t squared. Now cancel what's the same on each side. So those halves can go. They are also in the same time of flight tube, and therefore the distance that they are traveling is the same. So therefore the d's cancel. We are therefore left with an equation that is m over t squared equals m over t squared. Now we're going to put in the data that we know. So we have m over t squared equals m over t squared. So the ion that we know everything about is the 63 isotope of copper. So we can do 63 divided by its time of flight squared. That is equal to the 65 over the time that we don't know squared. Once we've done that, we can now just start to pop this into the calculator. So do the 63 over the 1.829 times 10 to the minus 5 squared. Then we're going to rearrange. So in order to find that equation, so it is t equals, you're going to swap them diagonally so that t squared is equal to the 65 divided by the answer the calculator came out with. Then it simply becomes a case of finding t on its own. If it was t squared, we're going to square root the other side, and that is going to give us our answer. Don't forget to finally consider the significant figures of the overall answer. And remember, for that, go back to the question and look at the data. Everything was to 4 significant figures, so our overall answer is also to 4 significant figures with the units. So some key points to take away with you from the practice questions today, especially around questions that use that equation. So remember, manipulating equations can be hard, especially if we're just beginning A-level as well. So make sure that you practice rearranging it in its different forms. So skip back to the part in this video where I talked you through those equation manipulations if that helps you. Secondly, make sure you learn the standard units as part of this equation so that you don't get caught out by forgetting to convert. Remember, the key point there is distance is in meters and mass is in kilograms, which often requires a conversion. Secondly, don't let a calculator error slip you up. If everything else is going right in your method, don't let a simple thing like forgetting brackets on the calculator giving you a wrong answer. And then finally, the answer that the calculator churns out at you is not always that final answer you want to be giving. You need to do a final little bit of processing that considers the significant figures required for the question, which is often the smallest number of significant figures that the data is given to you. And finally, also don't forget those units.
Thanks for watching, and make sure to subscribe for more new weekly chemistry A-level content, including walkthroughs, exam tips, and lessons.